Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk about real and reciprocal space lattices and lattice vectors that we have. We want to introduce the effect of the crystal on the electronic structure, and for that we have seen that we're going to introduce a periodic potential that represents the crystal lattice. And in order to be able to talk about this, we have to introduce a few concepts that we have in crystals and lattices that we have both in real and reciprocal space. So when we talk about a crystal, we can define this by first defining a unit cell. And the unit cell is that part of the crystal that is repeated periodically. The unit cell is defined by three vectors, A1, A2, and A3, that together define a parallel pipe. So some volume in these angles might be 90 degrees, they might not be 90 degrees. These vectors might be equal in length, or they might not be. But in all cases, this is a parallel pipe. We want our unit cell to have non-zero volume, so we do require that A1 dot A2 cross A3 is non-zero. And I would urge you to make sure that it is positive, such that we have a right-handed coordinate system. Naturally, we can write down all equations for left-handed coordinate systems. You can't write down the equations when the volume is non-zero. But when you have left-handed coordinate systems, you have to think about Lorentz law and things like that all of a sudden turn around. Your Pauli matrices, you have to redefine to make sure that everything goes right. So let's use right-handed coordinate systems. Now within a unit cell, we can have one or more atoms, and this defines the basis that we have in our unit cell. So the basis is the positions plus types of atoms. If we look in this case at 2 out of the 3 unit cell vectors, then we can have one atom per unit cell, and then the basis is just one atom. That atom can sit in the point 0, 0, but you could equally well put that atom at a different position in the unit cell, and that would describe actually the same crystal. Instead of one atom, we can have 2 atoms in the unit cell, which either might be the same type of atom or different type of atoms. When it is the same type of atom, you have to of course make sure that it's not sitting in some high symmetry position, which would just reduce the size of the unit cell. But when it sits at an arbitrary position, then it is this structure that is repeated in space and thereby defining the crystal structure. Now the last thing that we need is to be able to periodically replicate these unit cells, and for that we have the lattice vectors. And the lattice vectors define a Bravis lattice, and these are given by all vectors that can be written as integer multiples of the unit cell vectors, where Ni is element Z. So this defines a set R such that the lattice vector R is an element of that set, and the set only contains vectors that can be written in this form. So all elements of R are a vector that is a multiple of the lattice constants. So with that we have defined enough about crystals to work with within this lecture. Now when you look at crystals, they have a certain symmetry. The axis can be 90 degrees, you can be cubic or tetragonal, hexagonal. You can have different bases that gives you more or less symmetry options that you have. Within the examples that we will do during the lecture, where we derive the basic properties, I will normally make sure that we take these axes to be 90 degrees, that we look at one-dimensional systems such that all these symmetry arguments simplify a lot. I think that in those cases you can still see the essential physics. At the same point, I want to do and want to be able to describe some real materials. And real materials never order in simple cubic structures. Even our simple metals are hexagonal closed packed or BCC, so it's cubic with 2 atoms per unit cell at the face or in the center. It's basically the closest packing of oranges that you can make. And already there, additional symmetry arguments will enter, and Brillouin zones or real space unit cells will start to look slightly more complicated. For those cases, I will just do this on a case-by-case basis and explain what is needed. In principle, there are 32 point groups, so that is 32 different ways you can order the local symmetries in a crystal, and 230 different space groups, so there are 230 based on symmetry distinguishable unit cell and lattices that you can make, which already shows you that just by these simple definitions and the possible symmetry options that you have in 3 dimensions, you do get quite a rich physics and set of possibilities. But for this lecture, just the bare minimum knowledge on crystals should be sufficient. Now, we know that our potential is periodic. So V of R must be equal to V of R plus a lattice vector for all lattice vectors that are a lattice vector. We can now have a look at the interaction between 2 electrons with different momenta. So before we looked at V of Q, which was 1 over V, the integral over the volume, V of R e to the minus I Q dot R dr. Where we have to be a bit careful, this volume is the volume that goes to infinite. It is not the volume that we had before, which is the volume of a single unit cell. You have to be slightly careful of that, but in the end, it doesn't matter that much. We can now, or it's clear from the context where you work with the potential, and we know that it is periodic, so this should be equal if we just shift our potential, and as our volume is infinite, we can just shift the integration boundaries, and it stays 1 over V times the integral over the volume, and we take R to R minus a unit vector of R e to the minus I Q dot R minus capital R dr, which is, I can take this e to the minus minus R I Q outside, e to the I Q dot capital R, and then we are left with V of Q. So we find that we have 2 options for our potential. either the potential is 0 at this q vector, or e to the I q dot r is equal to 1. Well, this is the same as saying that the scattering vector between our two electrons dot a unit cell, a lattice vector is equal to 2 pi times an integer. We can now define the set of all scattering vectors for which this is true. So G is the set of vectors for which Q dot R is equal to 2 pi n. And this set of vectors again defines a lattice, which is our reciprocal lattice. These vectors can be written as n1 b1 plus n2 b2 plus n3 b3, where b1, b2 and b3 define a unit cell in the reciprocal lattice with an integer. And we can write these reciprocal lattice vectors as 2 pi divided by the volume, which now is the unit cell volume, times A2 cross A3. And we can cyclic perturb them, so B2 is A3 cross A2, A1, B3 is A1 cross A2. Or, if you wish, you can also write this as a matrix that you generate from the 3 vectors, and the matrix of the reciprocal units vectors transposed is 2 pi times the inverse of the matrix that you get from the real space lattice vectors. So each lattice in real space comes with a lattice in reciprocal space, and a unit cell. Defined by B1, B2 and B3. And we've seen that you only have an interaction if the q vector belongs to the reciprocal lattice vectors. So only 2 electrons interact with each other when their momentum is different by a reciprocal lattice vector. And this is a concept that we will use in the next video to see how we can derive or look at the electronic band structure of electrons in solids or in crystals. Thank you very much. We'll see each other in the next video. Stay healthy.